Hello everybody, welcome to this live session of the course Kinematics of Mechanisms and Machines. Here we are going to take questions from you. I hope more or less the course is running smoothly. The questions that you have from time to time we will try to answer here. Some of you have already posted your questions and I would start by taking these. Dr. R. Samuel Hansen, he has asked on what basis we have to choose one out of two solutions for the given assembly. So, how do you choose the solution that is relevant? Well, when we solve the problem mathematically, when we solve let us say inverse kinematics or direct kinematics, we usually solve an equation of the form let us say A sin theta 4 plus B cos theta 4 is equals to C, where A, B, C are functions of another angle theta 2. And theta 2 is known. The question is, when we solve for theta 4, if you remember we have discussed this, we get solutions of the form tan theta 4 by 2 is equals to something, and from here we typically get two solutions. In more complicated mechanisms we can get more solutions, as you have already seen in these lectures. Now, how to choose the solution that might be relevant? Mathematically both solutions or whatever solutions the mathematical equations give are correct, but physically there might be a choice. So, the choice comes from physical considerations. Okay. So, the choice of the solution comes from physical considerations. Here I would like to take a concrete example. You remember this example of the excavator, in which we had this kind of mechanism. This is the actuator and the bin was connected here. Now, if I tell you, if I give you the angle theta and I ask you to find out S, for example. So, for a given value of theta we are to solve for S. Now, there can be two solutions of S, as you have seen in these lectures. You now know that there can be two solutions. One solution, already I am showing this. Another solution could be where this goes something like this, and the actuator goes like this, and the bin can go in a very strange position, something like this. This will be the other solution. Now, this solution we never would use right, but mathematically this is a correct solution. Mathematics does not know the application of the mechanism, where the mechanism is being used or what should be the motion range for the bin. This the mathematics will not know, but from physical considerations you can choose this as the correct solution, the blue one as the correct solution, and you can discard the brown solution, the other solution. So, this is how you can choose solutions. So, based on physical consideration, it could be based on the physical limits of actuation. Actuator, a prismatic actuator mathematically can give any arbitrary amount of throw, but a physical actuator cannot give an arbitrary amount of throw. So, there is always a limit. Now, that limit has to be respected. So, based on these things, so essentially based on physical considerations, we have a valid solution or an invalid solution. Okay. So, this was this question. Then related to this course, we have been receiving different kinds of questions. Himanshu Gupta has posted a question on constrained motion, and he has also asked the difference in flywheel and governor. Now, flywheel and governor was not discussed in this course, but let me just give you an idea. Flywheel and governor apparently seems to work on the similar things. It controls speed of an engine, but you see the governor it is used to keep a constant speed, maintain a constant speed against varying loads. Loads can increase, the speed of the engine can go down, but it will increase the fuel and hence maintain speed. But a flywheel, it actually removes fluctuations from speed, and that can happen at any speed. It can happen at any RPM of the engine, any speed of the at which the engine is running. It will just take out the fluctuations, it will remove fluctuations from the engine output, whereas governor tries to maintain a fixed speed irrespective of what load comes on the engine. Well, the other thing was constrained motion. So, this also we have discussed in this course. Constrained motion is when the links, the relative motion between links can happen only in a particular way, and the example that I have given is, suppose I take my hand on a straight line up and down. So, the relative motion between my forearm and my arm is fixed. This is constrained motion, and it has got, you see, 1 degree of freedom. I mean, the way, if you think that this is a planar mechanism, this has got 1 degree of freedom. But if I make it 2 degrees of freedom, the relative motion between my forearm and my arm is not fixed, right. It can have arbitrary angles, and this can go to arbitrary x and y locations. So, this is what we mean by a constrained motion of a mechanism. So, constrained mechanisms have 1 degree of freedom. So, whenever we talk of constrained mechanisms, they have 1 degree of freedom. Then there is also a term redundancy. You see, redundancy comes in mechanisms for various reasons, and most of them are due to physical reasons. For example, if you have a parallelogram linkage, a parallelogram linkage, and if you want to move this through 360 degree, then there comes a configuration where it is uncertain. Now, what at this configuration, what can happen is this can go down and this can move up, there is a possibility. To remove this possibility or to prevent this uncertainty, you can use redundancy in the mechanism. by putting another parallelogram linkage. So, we have here this kind of a parallelogram linkage, two connected parallelogram linkages in fact, so that when one goes into this uncertain configuration, other one will maintain the parallelogram structure. Here of course, from mechanism point of view, this part is redundant, this part is redundant, this was not necessary, but from physical considerations we need to sometimes use redundancy to strengthen the mechanism or even to prevent these kinds of problems. Okay. Next we see if anybody has posted the question. It is not coming here.
So Google Chrome, first tab in Google Chrome. Rajiv,
Okay, here is a question from Siddharth Tiwari, how to find velocity of slider crank mechanism, it should be slider crank mechanism by relative velocity method. Okay. We have discussed a different kind of method in this course for velocity analysis, but we can also use velocity difference method, which you will find in various sources. Let me just illustrate this by a simple example. So, here so, this is a slider crank mechanism. Suppose you are given omega 2 and you are asked to find out the velocity of the slider. The way we have done is we have looked at the instantaneous center of rotation etc., and we have done the whole thing analytically. You can write down the equations and do it by velocity difference method. So, to proceed with this method, what you need to do is you have to start writing the associated equations. So, let us say I will write V b is V a plus velocity of b relative to a. Since omega 2 is given, I know velocity of a, I know the magnitude of this velocity as well as the direction of this velocity. V b, which is this, V b is the velocity of the slider. I know its direction, but I do not know its magnitude, and velocity of b relative to a, I know that it is going to be perpendicular to the connecting link a b. This we know, we had discussed this in a lecture, that for a rigid body the velocity of 2 points must be such that the projection along the line joining is the same. So, V b can be like this. So, the relative velocity must be perpendicular to A b. Relative, it cannot have any relative velocity along A b, because this is a rigid body. So, I know the direction of V a b, but I do not know the magnitude. Now, there can be various ways of solving this equation. The simplest, which appeals to us very quickly, or to everybody very quickly, is the graphical method. Let me quickly look at the graphical method. So, in the graphical method, we start by drawing the velocity of A. Now, with omega 2 given like this, you know that the velocity of A is going to be something like this. So, this is velocity of A, which is known completely. Now, velocity of B relative to A, I know the direction, which is horizontal, but I do not know the magnitude, but I know that, and I must add that to this velocity of A vector. Therefore, velocity of B relative to A must be along this dashed line, and velocity of B, this is velocity of B, this is velocity of B, velocity of B relative to A is perpendicular to B A. Let me first draw that. Velocity of B relative to A, I am adding to V A velocity of B relative to A, which is perpendicular to this direction. So, it is this. So, velocity of B relative to A must be along this dashed line, and velocity of B is horizontal, and these three vectors must complete the velocity diagram or velocity triangle here. Therefore, this must be velocity of B relative to A, and that must be equal to velocity. So, this vector plus this vector must be equal to this vector. So, this must be velocity of B. So, this is the vectorial approach for solving this. If you want to solve it analytically, that also you can do. You have to represent these vectors in a suitable coordinate system. For example, V b can be written as a vector form. V b can be written as V b I cap. Velocity of A can be written as omega 2 vector cross, if I call this as O, then O A vector, and velocity of B relative to A will be, if I call this link as link 3, then omega 3 cross A B vector. And then I represent all these vectors. Omega 2 can be written as omega 2 k cap, O A can be written in terms of theta 2. So, L 2 cos theta 2 I cap plus sin theta 2 j cap, plus omega 3 can be written as omega 3 k cap cross A B. Now, this has to be written as a vector. So, L 3 cos theta 3 I cap plus sin theta 3 j cap. Now, from displacement analysis which you have already done in the course, you can find out, given theta 2 at a certain configuration, given theta 2 you can find out theta 3. We have looked at these calculations. So, you know everything in this vector equation except V b and omega 3. These are the two unknowns, and this is a vector equation in I cap j cap. So, there are two actually in you will finally get two simultaneous equations to solve for the two unknowns, which you can complete. Okay, I hope I have answered your question. So, here I okay. Okay. So, here I have the next question from Mayur Thombe. What goes in finding the dimensions of a mechanism for an application? This is a question which we have not addressed in this course. This is called mechanism synthesis. Synthesis is a actually very interesting topic, and but in this course we have restricted ourselves to only analysis. As you know that we are trying to find out degrees of freedom, we are trying to do displacement analysis, we are trying to find out velocity, acceleration, even force relations, but we have not covered dimensions for designing or synthesizing mechanisms. The synthesizing is the proper term because designing would involve dimensional or strength design. Usually it means strength design. I mean, you will have to find out how thick the links should be, but synthesis is the proper term in kinematics that we do. It is an activity which gives us the dimensions of the various link lengths for making a mechanism for a certain purpose. Here in this course we have not discussed synthesis. It is a very involved topic and it is beyond the scope of the present course. Amit Chorge has asked, please explain solution of assignment 2 question 11. Okay, so this this question is you have a mechanism which is used to pour some liquid from a container. Okay. So, as I turn this handle, what we expect is this is going to rotate and it will pour out the liquid that is there in this container. Okay, so the question is on the ternary links in pouring snout. Now, the question is number of ternary links, right? Number of ternary links. The ternary links are those which have 3 kinematic pairs connecting to it. You remember that we start by counting the ground as 1, 2, 3, 4, right. So, yes, okay. Now, here if you think about it, that there are 3 connection points for from the ground has 3 connection points, then this actually the ground seems to be a ternary link. Similarly, this container also seems to be a ternary link, but you see the relative motion. So as far as number of links etc., these are concerned, the ground seems to be a ternary link, as well as the pouring snout seems to be a ternary link, because it has connections here, here and here, though here you have higher pairs. Okay. But then if you think about the kinematic diagram of this pouring snout has a rotation about this point. It has a rotation about this point, therefore, as if this point is fixed, right. So, this is an equivalent mechanism of this pouring snout mechanism. So, if you look at this equivalent mechanism, there is no ternary link, but if you look at the actual construction, then you can see these 2 ternary links, but have we answered this 2? So, if you look at the equivalent linkages, possibly you got you have a question regarding if you go for the equivalent linkage, then we do not, but if you look at the mechanism as such, then we have these 2 ternary links. So, I think if you look at it in these 2 perspectives, then you will understand why we claim that this has these 2 ternary links. Possibly you have looked at the equivalent linkage. Okay, Siddharth Tiwari, he asks by Icy method, can you explain velocity analysis of quick return mechanism? I am having problem for location of IC for slider with other links. So, quick return mechanism. Okay, so quick return mechanism looks like this. Let me first draw it. Okay, so this is the quick return mechanism. Now, you have asked using a method of IC, that is what he is asking. First you will have to determine all the relative ICs, which we do as follows. We will mark out those which ICs which we know. For example, I know 1 2, I know 2 3, I know 1 4, I know 4 5, I know 5 6, and 6 relative to 1 I know it is at infinity. Usually in a quick return mechanism, what is specified is this omega 2, and what we are asked to find out is this V 6. A very simple method can be developed based on IC if we can locate I 2 6. You can go in by a standard way of finding out all ICs and trying to figure out, let us say, what will be omega 4, which is of this oscillating link, long oscillating link, and then solving for the 3R1P chain, which consists of this long oscillating link, this connecting link, and the slider. But we can always try to locate 2 6. If we locate 2 6, then we can immediately find out the velocity of the slider 6, since we know the omega of link 2 and the relative. So, relative IC 2 6 I 2 6 will have the same velocity if it belongs to link 2 or it belongs to link 6. So, we want to really find out 2 6. Now, for 2 6, you see it lies on 1 2 and 1 6. 1 2 is this and 1 6 is at infinity. Therefore, it must lie on, let me use a different color, it must lie on this line, okay. Oh, by the way, I also know 3 4, which is also at infinity. Okay. Now, I have to find out another path from 2 to 6. I have to find out another path from 2 to 6. One is 1 2 and 1 6. I have to find another path, which I can do like this. I can find out two 4 by taking the paths 1 2 and 1 4 and 2 3 and 3 4. Okay. Let me try in this diagram with different kinds of colors. So, 2 3 is here and 3 4 is at infinity. So, it is this line, and the other is 1 2 and 1 4, 1 2 and 1 4. So, it is this. So, this is this point is I 2 4. So, I have located I 2 4, and I also need 4 6, which has two paths 6 5. So, 5 6 is this one and 5 4 is this one. So, it will be on this line, and it will also be on 1 6 and 1 4. 1 6 is at infinity and 1 4 is here. So, this. So, this is I 4 6. Now, I have two paths, one is 1 2 and 1 6, 1 2 and 1 6 is at infinity. So, this line and 2 4 and 5 6. So, it is again the same. So, once I have located 2 6, then I can find out. So, if I know I 2 6 somewhere here, then I know that the point on link 2 belonging to the I 2 6 as seen as a point on link 2 has the same velocity as the point on link 6 which has I 2 6. Therefore, extension of link 6. It looks like this, that this is link 6 suppose, and this is link 2 or an extension of link 2. Suppose I 2 6 is somewhere here. So, this is I 2 6, then the velocity is, this is omega 2, omega 2 times this length. So, omega 2 times O 2 I 2 6, this length, that is the velocity on any point on the rigid body 6 or an extension of rigid body 6. So, this must be equal to V 6. V 6 is horizontal. So, given these things, so once you have found I 2 6, you can find out that velocity of I 2 6 when it belongs to link 2, and that is precisely the velocity of link 6. And that is why you see it, this point I 2 6 comes on a line which is vertical from the hinge O 2. Okay. Then Rahul Malik, he asks, formula discussed in week 3 and 4 are difficult to remember. Will we get some sheet regarding these in test which is scheduled to be on 29th March? Okay, so these formulae that we have discussed in week 3 4. So, these are on displacement analysis formulae for the and the steering mechanism, the formula for steering mechanism. And in week 4 analysis of robots, geometric velocity analysis. Well, formula will not be provided. You will have to be able to work these out by yourself. Of course, it will you should not expect too complicated application of or remembering formula, etc. So, please do not think that we expect you to remember all these formulae and all these steps that go into the thing. We will test you for your understanding of application of mechanisms and simple things which you can possibly base your intuitions on in these I mean working out through the exercises etc. Because in exercises which are also part of evaluation, in that we have tested you for application of very complicated expressions or working through these expressions or deriving them and finding out the results, but in that final test we do not expect you to remember formulae. Okay. So, but your intuitions can be possibly based on these applications of these formulae, how the formulae come about. For example, the concept of IC, the concept of IC that we have been discussing, you should be able to find out velocity using a simple location of an IC. Okay. Okay, then the next question that has come up is from Siddharth Tiwari. What is mechanical advantage and transmission angle? In this course, though we have not considered this transmission angle, because that is usually taken up in synthesis. When you talk of let us say a 4R mechanism, typically this angle and it is usually called mu, this is the transmission angle. Why this is called the transmission angle? Now, when this angle, let us say this angle goes to 0, okay, so this is let us say the driver, this is the driver, this is where I will give my input torque and I will drive the mechanism from this hinge O2, and the load is at O4. So, it is driving the load at O4 and being driven at the revolute pair at O2. Now, if this so what is the significance of this angle? If you consider that all these links are massless, let's assume, make this simplifying assumption that all the links are massless. In that case, the force that gets transmitted you already have the concept of two force members, right? You have the concept of two force members. So, in a two force member the forces are always along the member. So, in this mechanism being driven at O2 and driving something, some load at O4, definitely the driving links or the driven link, they are not two force members, but the link AB, which is the coupling link, coupler, that is a two force member. I have made the simplifying assumption that masses are negligible. So, if this is a two force member, therefore, this force that is being transmitted by the coupler is along AB, and that force gets transmitted to the driving link, which is the link 4, and the angle that I have indicated, the transmission angle is mu. Now, if this mu is very small, then you can imagine that the transmission will not be good, it will not be able to possibly drive the output. But if the transmission angle is very large, then it is going to drive a lot of torque is going to be or the it can take a lot of torque by finite force at this hinge. So, this force is going to remain finite and it is going to handle the torque that comes, the load torque. On the other hand, if this link goes something like this, then the force is this and mu is almost close to 0, then it cannot resist this load torque, right. So, transmission will be poor. So, this is the significance of the transmission ratio transmission angle, sorry, transmission angle. So, this is the significance of the transmission angle. Okay. Here is another question by Amit Chorge. He asks assignment to question 6. How to apply Grashof criterion to the problem? Now, here the question is like this, that a 4R mechanism is shown and some dead center positions are indicated, something like this, right. Okay. Now, the question has suggested 4 possible answers, so you have to choose the correct one. These numbers are the link lengths, right, they are the link lengths corresponding to AB, BC, CD and DA, and these dashed lines are the dead center configuration. Now, here what is the first impression about this, that you see both the dead center configurations are on one side of the frame. So, this is the frame, line of frame. So, this is the line of frame. This is the line of frame and both dead center configurations are on one side of the line of frame, and there are dead and both links have dead centers, which means at least these two ground links, these two links, let me number them actually 1, 2, 3, 4. So, here it was named A, B, C, D. The links AB and CD do not cross the line of frame and they are oscillating links. In a this is typically a typical characteristic of a Grashof chain, that the rocker does not cross the line of frame, and here both are rockers, both AB and CD both are rockers and they are not crossing the line of frame. And definitely, I mean, there is AB and CD definitely they are restricted in their movement. So, they are rockers and they are not crossing the line of frame. So, this is definitely a Grashof chain. Now, if it is a Grashof chain, then there must be a link that is rotating completely. So, the only possibility is BC, right. The only possibility is BC is the shortest link and therefore, it must satisfy Grashof criterion, and where B C is the shortest link. Let us now look at the possible the options that are given to you. Options are 3, 5, 5, 2, 6, 5, 3, 5, 5, 2, 4, 5 and 5, 2, 2, 4. Now, this is BC means the second one is the shortest link. So, it should be one of these two and which satisfies the Grashof criterion. I think this satisfies the Grashof criterion because L min plus L max is less than the sum of other two links. So, this is your solution, and therefore, BC is the shortest link, and therefore, this is a Grashofian double rocker. Okay. So, this is how you can solve this problem. Okay, since we are running out of time, 3 minutes more. Standard question, okay. Some of you have asked whether we can use other methods to solve the problems in this course. This question has possibly come in the forum. Of course, yes. You are free to choose your own method, but here we have discussed certain methods. You try to also learn these methods, try to adopt. Some of them are very good for automating them or writing computer codes using these methods, but of course, you are free to choose your methods. Some of the other standard questions that have come up in the forum. Yes, this question there is a question. If we see the Kennedy theorem, the Kennedy-Aronholt theorem, it states that three bodies have relative motion with each other with instantaneous center on a line, but we also know that a 3-link system has 0 degree of freedom. How can we say that 3 links will have relative motion with respect to each other? This I will quickly illustrate. First of all, the Kennedy-Aronholt theorem says that 3 bodies in relative motion. It starts with the premise that 3 bodies are in relative motion, which means they need not always be connected. They may be absolutely 3 independent bodies. They can be 3 independent bodies which are in motion, both translation and rotation. They could be connected bodies, of course, like this, but it could also be this, as you possibly have in mind. This is what possibly you have in mind, this one, but then there is no relative motion, and it also does not satisfy the Kennedy-Aronholt theorem. You see the relative ICs are not on one line, so definitely this will have 0 degrees of freedom. But Kennedy-Aronholt theorem is not to be used in the inverse sense so for applying Kennedy-Aronholt theorem to this mechanism is applying it in a reverse sense, that if Kennedy-Aronholt theorem is not satisfied, they cannot be in relative motion. So, that is what this mechanism tells us. But otherwise, Kennedy-Aronholt theorem has to be applied when 3 bodies are in relative motion. It could be absolutely free motion like this example, or it could be this, or some connection where relative motion is possible. That is the first basic requirement. Now, if you see this third case where it is not possible, you see the relative ICs are also not on one line, and they are fixed. The relative ICs cannot come on one line. But where the relative ICs can come on one line, this example possibly has been answered to one of the questions in the forum. This has come up. Here this is relative IC, this is relative IC, and this is rolling. So, this is a relative IC. Now, these relative ICs are all on one line, and these are circles. My drawing does not seem like circles. Okay, so, these are perfect circles like pitch circles of the gears. Then the relative ICs are this, this, and this, and they are in a straight line, and they always remain in the straight line. So, motion is possible in this particular case, even with pure rolling. Of course, if you allow sliding, then motion anyway can take place. In that case, this is not the relative IC at the center. Relative IC will come when there is pure rolling, then it is relative IC at that contact point. Here it always remains, but if you do this with links, if you join this, if you have links like this, you try to move this slightly, this IC will shift from its position, and it will not lie on, this is an exaggerated diagram, it will not lie on the same straight line. So, it will refuse to move beyond a certain point, but there is a little possibility when it is exactly on this line, then there. So, this is actually some kind of a singular configuration. Anyway, so I hope I have been able to answer some of these questions. If you still have doubts, please get back to us through the forum, and you can always write to us with all your doubts. So, thank you.